experimental program here.
No.
Master's.
All right, so let's do repeated measures designs. Hold on to that story for later. It sounded very exciting. Mostly chapter 13, a little bit of chapter 14. And this is where we have to get really specific on terminology. So that question that you had on both of these last assignments, what type of post hoc test is it and why, now it's going to be important. So anytime we talk about between subjects ANOVAs, those are independent ANOVAs. Independent T is the follow-up, where each person only gets one of the levels. Okay, so everything we've done so far has been independent. Repeated measures, sometimes called within subjects, sometimes called dependent or paired, which is really frustrating to me, but those are all the terms that you will see for repeated measures, where everybody gets all of the levels. Next week, what we're going to cover is mixed designs, where you get one of each, and then I think we have a test. So, and the whole next test is ANOVAs. But we're getting into repeated measures today, and we'll do mixed next time. And the problem with repeated measures ANOVA, or not really problem, but the issue is that the levels are going to be correlated. So I have the same person taking these different tests, and at minimum, they'll at least be correlated because they're the same person each time. Sometimes levels are not correlated because they're so different. But in general, we have to assume, since it's the same person, we're doing there's something there. And that violates the assumption of independence. So since everyone was a separate person, independence was more of a question of research design. Does something happen in the experiment where they're tied together? But now we don't have independence. They are tied together. So I got to deal with that in a special way. But the nice thing about repeated measures is that they're very sensitive, which means that they get more bang for your buck for each participant. So generally I recommend repeated measures if you can. And anytime you do survey designs, it sort of naturally is a little bit of repeated. So we're going to reduce unsystematic variance. That's the error variance, or the messy stuff, bad variance, which allows us to be more sensitive to these experimental effects. Because what happens is that we're going to reduce the peopleness factor. So there's still an error term, but we're also going to take out error, like the correlated people part. So I'm going to call this the peopleness factor because unfortunately the term the books use is confusing. Okay. But we're going to remove the variance due to it being person A the entire time. The best way to think about this is like class grades. So if I'm trying to manipulate class grades, obviously I want them to go up. There are some people that are just C students. Some people that are A students. So I can control for the fact that they already start in different places. Repeated measures ANOVA has more economy. I need less participants for the same study, and now we actually did an example of that in t-tests. We talked about the exact same data. If I did it with between subjects, I needed a lot more participants. If I needed to do it with repeated measures, less participants. But research design-wise, you have to be careful of fatigue. So you don't want to give them too much to do, or they'll get bored and want to quit. Right. So coming back to sporicity. So we've been talking about homogeneity, Levine's test, of multiple days. Now let's get into sporicity. We did this a little before. We talked about sporicity is a dumb assumption because sometimes the research design pushes you to not have sporicity. So remember we talked about smoking cessation. You want people to quit. It has a natural floor. They cannot smoke negative cigarettes. So the variance is going to naturally decline as people go closer to the floor. Also with weight loss, there is a bottom level where people shouldn't lose more weight. Right? So I'm going to tell you how to check for sporicity, and we're going to talk about how it works and the rules for it in case someone asks you to do a sporicity correction. But in general, it's sort of a tricky assumption because sometimes your study just will not meet that assumption. So what is it more detailed now? It's that the levels that you have a similar relationship. And we have what's called compound symmetry. Put a star here. I like to ask this question. What is compound symmetry? So let's say I have 3 levels. For whatever we're testing. Today we're looking at Halloween costumes because it's almost Halloween, and the ratings of different beers and wines, because it's Monday. Those are from the book, though. It just happens to always fall right on Halloween, so it's good timing. And we have a couple of different levels. So we might go to a haunted house, we might go to a house party, or I think one of the options is small costumes, so it might be too cold, although not this year, since it's like nearly 80 today. The first requirement for compound symmetry is that we have similar variances. But, here's the big caveat, it's not this. So with homogeneity, right, it's that the variances, we're using SD. Is that the variances are equal. So the standard deviation for each group is roughly the same. Not for sporicity. So for sporicity, it's that the standard deviation of the differences is equal across groups. So this is 1 to 2 is equal to 1 to 3. And in this particular example, SD diff 2 to 3. That is an entirely different question. Do the individual variances for each level be the same? Instead, what we do is subtract the two levels and calculate the standard deviation of the difference scores, which we did for effect size, just showing you how the difference works. So there are variances, the difference score variances are the same. Why are they so different? Well, for homogeneity, these are different people, so it doesn't make any sense to subtract them. But for sporicity, it's the same person multiple times, so I'm actually testing their change between levels, if that variance in the change is the same. So that's why it's hard to meet sporicity if we're doing like a weight loss. Right? Everybody's going down, and then they level off. Big change here, no change here. So we've already validated the assumption of sporicity. But that's what you wanted to have happen. So, the other thing for compounds, so there's two parts, is that the correlations are similar between levels. So we're saying R equals R equals R. So 1 to 2 is the same as 1 to 3, same as 2 to 3. So sporicity technically has two parts. It's testing if the standard deviation of the differences is the same and if the correlations are the same. So that's where the term compound two-part symmetry is. All right. So we should kind of have like a base. You won't have to ever like do this by hand. We're going to use Mauchly's, but that basic idea is important. So the test for sporicity is Mauchly's. You will get it automatically as part of ezANOVA, which is why we like ezANOVA. And it's an ANOVA on the differences, and that's this part I was trying to get at. So not an ANOVA on the variances, an ANOVA on the variance difference scores. All right, but the output for Mauchly's looks pretty much nothing like the output for Levine's, because consistency is not a thing that statistics does well. So we'll talk about how to read that output. Another important thing, there's no sporicity if you don't have two levels, because we didn't talk about sporicity at all for dependent T on purpose. Okay. So why? I also really love this question, like a lot. And every year it's like half the people remember that I've said I love this question, half the people just write like question marks. If I only have two levels, and it's an ANOVA on the difference scores, how many difference scores can I have with two levels? 1. And I can only have one correlation. So basically don't have anything to compare it to. So it's just 1 to 2. So with only two levels, there are no difference scores or correlations to compare. There's just one. And with ezANOVA, if you have two levels, it shows you no Mauchly's. So if you're like, why did I get Mauchly's? It's because it only had two levels and it just can't even run. So, why won't you get it? Because it only has two levels. Every example we're doing today has more than two, so you'll see it. But I think some of the homeworks only have two. So don't be like, ah, I broke something. I'll go back and be like, you should read this slide and look at your answer. Okay, we've covered this already, but just so it's in the slides, it's hard to meet the assumption of sphericity. A lot of people ignore it. I don't know if we should totally ignore it, but if you have a design that forces data to the floor or ceiling, it's very difficult to meet. And what does ignoring it do to us, other than reviewers saying that you don't know what you're doing? It actually lessens power. So the less the correlations are between the time points, the lower the power. Because you sort of assume that they're going to be correlated since they're the same people. And we'll find type 2 errors are okay. So type 1 is where you said something happened and it didn't. We don't like that so much. Right? But if you missed something that happened, we find that more all right. Because remember, we set that to 20%. That's why power is 80%. Beta is 20. So we find those more acceptable than saying something happened when it didn't. And that's why alpha we set to 0.05. So it's a loss of power with sphericity. But I'll tell you how to correct for it, in case somebody asks you to. A little bit on data screening. And so you're still always checking accuracy and missing outliers. You might be able to fill in missing data, but I'm hoping that you don't have 20 columns that you're doing repeated measures on, because that's a lot of data, but you might. The last two sections we've had to do z-scores, because we only have one column. Now we should screen in wide format. So leave the data in wide format. Why? If you melt it first, it's still 1 dB. It's in wide format, but it's 1 dB, one set of scores that you're measuring across different conditions. But if you screen that in long format, you're ignoring the fact that they're correlated. Right, so we want to screen in a way that doesn't assume independence. So part of MANOVA calculates cove. It says cove in the code, and that's looking at the covariance between columns. So it's controlling for the fact that it's the same participant over and over again. So if you can help it in repeated measures format, screen in wide format. Okay. So data screen first, then melt. Which is what we talked about for t-test too, but we hadn't really tried that yet. Now we're definitely going to screen, then melt. You do have to check for additivity, but not in the same way. So additivity is really only a problem if they're perfectly correlated. Because mathematically perfectly correlated columns are not a good idea. It's like trying to divide by 0. So we're really just checking to make sure R is not 1. The old rule is 0.9. A lot of these things are going to be very, very correlated because you're asking them to do sometimes the same thing over and over again. So I expect them to be correlated. So the rule is much higher just so it'll run. And honestly, sometimes I only use additivity to run G-power. And I'll just kind of look real quick, make sure nothing looks bad. And then if it blows up when I'm trying to run it, I'll go back and look at this a little harder. Because one time we reverse coded a column for a scale, and they misnamed it just slightly. So it created a new column in the data set, and I wasn't paying quite enough attention because we had 900 columns. And we were trying to run Mahalanobis, and it just was like, nope, nope. Like, what is wrong? I finally figured it out, right? Because the correlation table, that symbols for numbers table, was so large it was hard to see. I finally dumped it into Excel and found that one typo. So the capital letter R gave us some serious trouble at one point. If you're going to reverse code items, this is one place that you might be able to see that you did something. Type something wrong. Still got to look for normality. Still needs to be linear. Homogeneity, but not Levine's, Mauchly's, and homoscedasticity. Often problems with Mauchly's will give you homoscedasticity problems too, because the spread of x down y might decrease or increase over time. All right, so what do I do if I violate sphericity or some of these other assumptions? We talked last week about a one-way test, or 2 weeks ago, excuse me. You can do the corrections. We're going to talk about the corrections. So it'll be your spelling words for the day. MANOVA, which is a different form of, it's like between subjects ANOVA, but with lots of DBs. Or it can be a double repeated MANOVA. It gets really tricky. So MANOVA, or sometimes it's called a, starts with a P. Sometimes this other analysis that starts with a P that's similar to MANOVA. It's going to come to me in like 3 hours. Anyways, or the newest and most popular thing is to do multi-level model. And we had this joke in our research lab that it's like, hi, you're new here, that's great. Here, learn this really hard statistic and later we'll explain it to you. Because we do lots of multi-level models. Because repeated measures ANOVA has its issues. And multi-level models allow us to control better for the correlation between people and the fact that they start in different places. So sometimes you want to deal with the fact that some people are C's and some people are A's. And some MLMs are slowly taking over regular repeated measures ANOVA. Okay, so by corrections. Because we don't have time to cover MANOVA and MLM. If you're really interested in that sort of thing, next semester I teach an advanced class that covers, next year I'll cover both of those. Okay, corrections. So unlike post hoc corrections, which are corrections on p-values or alpha, these corrections are on degrees of freedom. So if you've ever done one of these in SPSS, it actually gives you the partial degrees of freedom, but it doesn't in ezANOVA. I'm not entirely sure why, it just doesn't. But what that does is it affects the cutoff score. So if I have 30 degrees of freedom and it goes, yeah, no, you shouldn't have that many because this is really a mess for sphericity, it like subtracts some of my degrees of freedom. The smaller the degrees of freedom, the further out you have to go. So remember our little magic Scooby-Doo bus has to cross the finish line. The Mystery Machine. Yeah. If we make the finish line further away, it's harder to reject a null. Okay. And so lower degrees of freedom gives you more of a type 2 error because it makes it harder to reject. God, stumbling today. Two main corrections. Greenhouse geyser, that's how I've always heard it said. I'm probably wrong. And Hunfeld. So big two. I'm going to abbreviate these GG and HF from here out because they're not easy to spell. Which one do I use? Okay, this is not going to make any sense on this slide, but once you look at the output, maybe hopefully it'll make a little more sense. The sphericity correction is called epsilon. Okay, that's what little e is. And that just means their estimate of sphericity. Okay. If that estimate is over 0.75, it ranges from 0 to 1. You're going to use Hunfeld. If it's less than 0.75, use greenhouse geyser. Right on 0.75, I don't know, flip a coin. So we want to pick the Hunfeld, which is less restrictive. It's a more easygoing test, if you will. When sphericity estimate's very high. When the sphericity estimate is really low, which means there's not a lot of sphericity, we want to use the greenhouse geyser, which is a bit more restrictive. Okay, so let's try an example. So these, hopefully some of this will make a little more sense, more concrete. So our silly example for the day is, are some Halloween ideas worse than others? Yes. Right, so we've got 8 participants, not a very big data set. We can't really assume normality. And they actually tested all 4 ideas. So they went to a haunted house, they wore a small costume, a punch bowl of unknown drinks, or a house party. And they rated it on 1 to 12, where 12 was that this was a really dumb idea, shouldn't have done this, and 1 was this was a lot of fun, it was fine. And so before we get into like importing the data and actually doing something with it, we've been trekking along this path about talking about sum of squares. This is in the F table explained document, but the one for double repeated measures is not, because you just don't want to know. Back to our cookies. So we have this pool of cookies, total variance, and we're going to break that down. This is the new thing over here. this SSB thing, which is impossible to read. So let's break it down one piece at a time. So sum of squares total, this is all of our cookies everywhere. This hasn't changed, so you really shouldn't miss this one on the test. It is always mean minus the gram mean, always, okay, no matter what design we're talking about. So mean minus that gram mean tells me how much variance there is total, ignoring levels, okay, or conditions. Then we're going to break that into between and within, and this is where the terminology is really poor, because often between and within, people talk about those as good variance and bad variance. That's not quite what they mean here. So we're breaking this down into sort of SS repeated measures and SS people. So sum of squares within, this isn't model quite yet, but it's mean minus my level mean, which is very similar to model, right? We've been doing that for model, mean minus my level. But the problem is that I'm in each of one of those levels. So you've used mean multiple times. You've got to control for that somehow. So with that sum of squares model, or sorry, sum of squares within, I'm going to break that down into model and residual, and these are the same. So model is my level minus the gram mean. That's the same as between subjects ANOVA. And residual is everything left. Residual used to be mean minus my level mean, but that's here, so we can't use it again. So kind of what we've done, it's hard to draw repeated measures. Let's see. So we've taken our huge vat of cookies. We haven't talked about what happens over here yet, but we sort of said a lot of these cookies should go over here. Mean minus my level. That used to be error. If you look at all the other math formulas for ANOVA, mean minus my level is a mistake, right? But now we're really interested in the fact that we're using mean multiple times. And we've made our own little separate batch of cookies. Breaking that down into level minus the gram mean. This is good variance. Yay. And then left, whatever's left. This is bad variance. So the way this matches between subject and ANOVA is this was the old version for error. But now, because people are correlated, because they're the same person multiple times, that's actually not error anymore. It's partially error, and partially due to the fact that they've taken multiple levels. So we're cutting out the part that's due to the multiple levels. That's the good variance, the good stuff. And then everything else left is bad. Logic-wise, before, these two things were very separate. Right? These people were different people. So we could treat them as separate formulas. But now, since the same people are in multiple levels, it's like tied to the bigger vat of cookies, so to speak. That's not going to work. And so I try to explain that in English. What's left over after calculating how different I am from my level, and then how different my level is from the gram mean. Remember, this is still me minus G. Model residual. So what's this other thing? So the book calls this SS between. This is actually the traditional term for this. I hate this term. Because we've used that term to mean model before. So this is where, to me, all the terms start to blend together, and it's unfortunate. So we're going to call this peopleness. That'll hopefully help you distinguish. Because we've talked about between subjects ANOVA, between subjects variance. Right. So sum of squares between represents that individual difference between participants. So you can see why I call this peopleness. Okay. And what it is it's a measure of how much people vary within levels. But that isn't the fact that I'm in multiple levels. So this is controlling for, this part here controls for the fact that I'm in several of these levels. This part controls for the fact that people are just different, but we're measuring them multiple times. And so it's kind of like how much variance there is by level, but it's more complicated than that. That's why the formula is actually not even in the book. This is the formula they give you in the book. So the stacked, the way I think about this is that this side controls for the fact that I'm tested more than once. This side controls for the fact that people just start in different places. So peopleness. Oh, and then we'll give it 2 cookies. But we started this lecture with repeated measures are more powerful because normally you only do this side, right? You only have a model and residual. But now we're also partitioning out peopleness. So we're actually getting rid of bad variance, and this variance never gets used, it gets tossed. So we've eliminated bad variance kind of twice. So repeated measures is more powerful because it has this extra component that just gone. And so I tried to summarize that all here in the table. This is the one from the Word document online. So individual differences between participants, right? And then the within part is the differences within participants. So that's why the names are between and within. But, okay. So peopleness. And then you can think about this as like figuring out the model. All right. The rules are still the same though. You divide going across, add going down. But only thing you're going to see on the output are these 2 rows. You actually never see between, ever. I mean, I can figure out within, I just add them together. So it's nearly impossible without doing some of this math by yourself. To get a total out of a program. SPSS kind of will show it to you, but they hide it in a weird place, and it's pretty confusing. And so we're actually not going to do omega anymore, because omega requires that you have some of these numbers that are just miserable to calculate. Because if you look at the formulas I've given you, we can figure out within. And I think we could probably figure out total, but then we'd have to backwards configure between, and it's not worth that trouble. So this is one reason I don't really love omega, is because it's really difficult for repeated measures. If you're flipping through the book, he says like, let's just not. So I'll show you the formula and then we'll not. Okay, so that is a good place to take a mental break.